Hello and welcome back to this lecture series. For today, we would like to look at homogeneous systems. Homogeneous systems. Now, a homogeneous system is simply a linear system of equations for which the right-hand side vector b consists entirely of zeros. Okay. Remember, our general form was ax equals to b. In this case, if b equals to 0 vector, then this system here is homogeneous. Please note that the entire b has to consist of zeros. If one of them at least, if at least one element in b, then the b vector is not 0, then the system is non-homogeneous. Alright? Okay. So what else? So today the purpose is for us to look at some of the elementary aspects concerning these homogeneous systems. Okay. Whenever, maybe something we will need to note here is that whenever a homogeneous system if a homogeneous system is okay, I'll come back to that in a bit. Okay, let us state right now that if, I think I mentioned this previously, that if we have the solution, if we get the solution at x equals to 0, i.e. x equals to the 0 vector, we say that we call this the trivial solution. So sometimes the homogeneous, under certain conditions, this homogeneous system will give rise to the trivial solution. However, it is not the case that at all times it will give rise to the trivial solution. Okay. So now we may be interested in knowing that are there solutions other than the trivial solution? Well, I'll say that yes, they are there. So if so, how can we best describe them? So as usual, we shall start with our Gaussian, and then we see how we can best describe some of these solutions to the homogeneous system. Well, let me explain what I wanted to say with the use of a simple example here. So we have an example. Okay. So we have an example of a linear system, ax equals to b. So I am going to write down the augmented matrix here. Okay. Now it is okay, we have ax equals to 0. Okay, the linear system x equals to b, where ax equals to 0, we have this homogeneous system which we are going to solve. Now it is kind of funny if I say that I am going to write the augmented system here, because the b is the 0, so that means that I would have to write a and then this whole side is zeros. I think that is just a waste of space and time, because there's nothing that's going to change if it's all zeros. So it is as good as saying, let us just have our matrix A and then we reduce it directly using our Gaussian elimination. Okay, so I will write down the matrix A, which we have 1, 2, 2, 3, and then what else? We have 2, 4, 1, 3, 2, 4, 1, 3, and then we have 3, 6, 1, 4. Okay, now let us reduce it quite quickly. Okay, so we would say we put R1 in row 1, we replace it there, 2, 2, 3, and then what are we going to put in row 2? We are going to put minus 2 row 1 plus row 2. So multiply by negative 2 and add, we have 0. Multiply by negative 2 and add, we have a 0. Multiply by negative 2 and add 1, we have negative 1. Multiply by negative 2, that is negative 6, and add 3, we have negative 3. Okay, and then what do we put in row 3? We are going to put minus negative 3 times row 1 plus row 3, and then we put the result in row 3. So negative 3 multiplied by negative 3 and add, we have 0. multiply by negative 3 and add, we have a 0. Multiply by negative 3, that's negative 6, and add 1, we have negative 5. I hope I'm not making any mistake. And then multiply by negative 3, that is negative 9, and add 4, we get negative 5. Okay, great. What else? Row 1, replace in row 1, so we have 1, 2, 2, 3. Oh, remember that in the first step we took our 1 here to be the pivot. Okay, so we eliminated everything below it. So in the next step we see that this is going to be our pivot, so this is our new pivot, and then we would like to eliminate everything below it, so row 2 remained as it is. And then in row 3 you can see we want to eliminate, well, if we want to eliminate this to a 0, we simply multiply this by negative 5. Okay, so we have negative 5 times row 2 plus row 3, and then we put the result in row 3. No prizes for guessing. This is a 0, this will be a 0, then multiply by negative 5 and add negative 5, we have a 0, and then multiply by negative 5, we have positive 15, add negative 5, we have wait a minute, okay, oops, I think I made an error. Oh no, I don't know why I keep on making these silly mistakes. This here, okay, let's check this again. This was a multiply by negative 2, that is negative 4. Okay, multiply by negative 2, this is negative 4, and add 1, this is negative 3. Oh no, why do I do this? Don't like this. Okay, so this is going to change. And what does this change? So we multiply, okay, we multiply times 5 over 3, or negative 5 over 3, multiply times negative 5 over 3, negative 5 over 3, row 2 plus row 3, and then we put the result in row 3. So when we multiply by negative 5 divided by 3, so we see that, what do we get? Okay, is it? Yes, we get a positive 5, and then add to negative 5, we get a 0. Okay, that's fine. And then, oh, it's the same, we'll also get a 0 here. Okay, like that, and then a 0 here. Okay, so this is our reduced row echelon form. Row, not the reduced row. Okay, start simply row echelon form. Okay, so remember that we have the right hand side vector has the zeros, okay, which we didn't write because it was just a waste of space and time. So we see that for such a system, now if we can maybe do back substitution, we can do back substitution for this first example, but in the subsequent examples there is no need to do back substitution. We can always analyze, but since this is the first example for this, let us do back substitution here, and then we see. So we can write down that equation. That equation will be x1 plus 2x2 plus 2x3 plus 3x4, and then remember on the right hand side we have 0. So this is a 0, this is a 0, and then this is negative x3 minus 3x4 equals to 0. Of course, now this consists of zeros, equals to 0, so we have no equation there. So now we have a scenario here where we have how many equations? We have 2 equations and 4 unknowns. Definitely we know from our elementary algebra that if we have more unknowns than the number of equations, then we cannot get a unique solution. Okay, we have no unique solution here. This system here has no unique solution. Remember last time we said it is consistent, the only thing is that it has no unique solution. Why? Because the number of equations, okay, let's say the number of unknowns, which we represent by n, is greater than the number of equations, which is m. Remember, these are the number of equations, and then this we say is the number of unknowns. So how do we solve this? There is a convention which is used to solve such systems here. Okay, the convention here is that we are going to pick what we call the basic variables, and then we are going to also, then the ones which are not basic, this time around we refer to them as the free variables. Okay, so there are several possibilities of selecting a set of basic variables. However, the convention is for us to use the unknowns which correspond to the pivotal positions. So if we go back to our row echelon form here, we see that the pivot here is 1, okay, and the unknown that corresponds to that pivot there is x1. I hope you will agree. And then the other pivot, which is -1 here, the unknown which corresponds to this pivot is x3. So we are going to let x1 and x3 be the basic variables, okay, and then the rest, which we have, of course, x2, use a different color, x2 and x4. These ones are going to be the free variables. Okay, so what we do, we will express the basic variables in terms of the free variables, right? So we say that we express the basic variables in terms of the free variables. Okay, so now let's start with this equation here, this one here. So for this one, we have said that x3 is the basic variable. Why is it the basic variable? Please remember, we say that because it corresponds to the pivotal element, which is this one here, -1. Okay, so we shall write x3 in terms of x4, and no prizes for guessing that for that one we have that x3, we have that x3 equals to 3 times x4. Okay, x3 equals to, so do we have, okay, x3 equals to 3 times x4. Just a minute.